Okay, so from time to time, we're going to want to define our own types in our program. So for example, we can define unsigned int to be a user-defined type called num. And this is a user-defined type. We use typedef, tell it what type, and then give that type a name. So now I can declare n to be a number. Actually, let's call this x. And we can set it equal to 10. And we can print out x is equal to some number. And we didn't call it num, we called it number, or we called it num. Let's call it number, since that seems to be what we like to use. And then save it once I make the change. Okay, so if we run this, we get x equal to 10. Now C now has a built-in Boolean type, but we could define our own if we wanted to, using an enumeration type. And so we can create a Boolean variable now. Let's print out what that is. Since there's no control sequence for a Boolean type, so we'll just print it as an integer. Then we'll set it to true and show that the value will change. My problem is here, I didn't spell typedef correctly. And you can see false is 0, true is 1. The reason for that is that in our enumeration, false was first, true was second. It starts with value 0, and then it increments by 1. Now, if I want to specify what those numbers are, I can say num1 equals, say, 3, num2 equals 10. And I need to give it a name. I'll call it nums. And we'll print out what that is. And I'll also print out the valid values. Which will be num1, num2, and num3. So you'll notice 3 I assigned to be 3, num2 I assigned to be 10, and then num3 I didn't assign anything, so I gave it one more than that. And I believe that that's what the standard is, but typically I recommend not relying on that. If you're going to do something like this and those numbers mean something, go ahead and just do the assignment. But one other thing, just to show you, since with is it true, it's a Boolean, and false is 0, which evaluates to false. I can say if is it true is equal to true, I can say it's true. In my else case, or actually let's still do an if. Let's do an else case. Let's say if not is it true, we'll say as if it is false. In fact, you probably should do this in both cases. Both cases, 1, 2, 3, 4, that's 6 lines. So I'll copy those 6 lines here just to show you that false and true both work as you might expect. Okay, so that looks good. I'm happy with everything so far. Now let's talk about structures. So here's a structure. I'll just call it a struct. And I can put whatever I want in here. I'll just put 2 integers. So that's one way to do a struct. So now if I declared a variable of type struct a struct, it would be a composite data type with 2 ints in it. I can also use typedef. And remember, now I tell it what type, and that type is going to be a struct with an int, a Boolean, and I'll also put in a string. And now I need to give this type a name. I'll call it my struct t. Now the difference here is in how I declare these variables. Actually, let's declare struct first. So there, the type of struct1 is struct a struct. If I just said a struct, it wouldn't work because that's not a defined type. When I do typedef struct, then this type definition is assigned to this type. So I can say my struct t, and I'll call it my struct 1, or my struct 2 is equal to 10 true and hello. And this initialization makes things a little easier. If I didn't do it this way, I would have to do a string copy into the s field of my struct 2. I can also declare a variable to be of a struct type, and I can define the struct in the declaration. So 3 ways to declare structures. The downside here is, of course, is that I have to know what this structure is, and I can't really carry this information around. Whereas for my struct 2, I know that that's of type my struct t, so I know what its structure is. This one, if I use this as a parameter or something, it becomes a little tricky. And there's things we can do to get around that, but we're not going to discuss those for this class. Let's print the structs. So to print my struct1, we have 2 numbers. And to access those fields, we use dot notation, my struct1a, my struct1b. My struct2 has a string as the third character, or the third field. So we have n success, and I believe that's all correct. And for my struct3, we have two variables. So let's print these out. It looks like my struct is undeclared. Looks like I got lazy with that. Okay, so there's all the things I initialized those with. So if I want to change things, I can say something like my struct1a is equal to 2 times my struct3y, my struct2n is equal to 30, and I can copy a new string into the s field there. So I can say my struct2.s. I'll just say go. And it's 16, so I could say 16 if I wanted to, but go is only 4 characters, so I'll just say 4. Notice 4 is fewer characters than is already in that string. It's hello right now, which has 7 characters, one for the 5 letters of hello, the exclamation point, and then the null terminator. So we'll see what happens there. So let's go ahead and reprint everything again. So now I'm just reprinting everything after I've made these changes. And I need to include string.h because I'm using string copy. And when I print this out, you can see the results. Why are the rest of the letters of my struct's string gone, right? We only overwrote 3 characters, H-E-L. What about L-O exclamation point? Well, when I did the string copy, there's an implicit null terminator in the string literal. So the 4th character is now the null terminator, which indicates the end of a string. So I don't have to worry about deleting the rest of those characters, although keep in mind, they probably are still there in memory. So if I, for some reason, overwrote index 3 here of this string with another character, I would see the hello characters again, or the rest of the characters of hello. Okay, there's one other kind of composite type we want to talk about, and that's the union type. Now here we have a struct, and I'm going to copy that as is, but I'm going to change it to a union. And I'll declare a variable for my union, but we'll use it later on, later down the road. And I better change the name of this type. And unions can kind of be tricky. So let's see an example. So I'm going to try this and see if this works. I haven't actually tested it on this system yet. But I'm going to do 43 or 44, 43, 42, 41 as a hexadecimal number. So since my union had the same fields as my struct, let me just change that my struct to thing. So we're going to print my union's n, it's success, and it's my union. And then let's print this out. So here we go. It looks like we have the same two values. If you remember though, that's a Boolean type, so we would only expect 0 and 1 there. Also, this is ABCD, which is a very weird number to get, or a random pattern of strings. And it turns out it's not random. 41 is the ASCII value of capital A, 42 is the ASCII value of capital B. And if you look here, you'll notice when I enter this in as hex, I'm basically putting a hex 44, a hex 43, a hex 42, a hex 44, or 41 into memory. So when those get translated as a string, I get these characters. And we'll talk about why the order had to reverse. That has to do with big versus little Indian. We'll get into that later in the semester. But the thing to keep in mind here is with a union, you don't get 3 fields. You get 1 field that can be used as any of these types. But whatever bits are in that memory location, those get interpreted. So since those bits happen to be valid bit patterns for a number, this is a D, this is a C, this is a B, and this is an A, it was able to read that out. Now, if I just put a random number in here, it's unlikely it would be even, it's possible it wouldn't even be a printable character or printable string once you converted each of those bytes into characters. And so that's why I did this as a hexadecimal to show that that would be that particular value. If I do this, and then print that again, you see now I get 0, 0, and then nothing because false is 0. That's a null terminator. As soon as it sees that null terminator, when it treats it like a string, it's empty, so it doesn't print anything. And then finally, I'll do those characters. And I think 10 should cover it. Let's print this one more time. Notice I get some random numbers here. I'm actually going to print this as a hexadecimal so that I print it out byte by byte. And if I do that, I get 34, 34, 34, and 78. Now it turns out that hexadecimal value 78 in ASCII is lowercase x, and hexadecimal value 34 in ASCII is 4. So I'm getting the x, a 4, a 4, and a 4. That's what this number is. That's what those bytes are. So when I treat it as a integer, I get that byte pattern, but it's actually the characters 4, 4, 4, x. And again, you can kind of see it's in reverse order. That has to do with how the words in memory are stored, and we'll get to that later in the semester. So why would we even have a union type? Because it's just a type that can hold one type, even though there's room for 3 different things. There's not going to be room for all 3 at the same time. It's big enough to hold any one of the 3 at a time. So let's print the sizes of these data structures. X is enum. So struct a struct. And my struct3, if you'll remember, was defined that way. And then finally the union. Okay, so let's print this or execute this to see what happens. Looks like I'm missing a parentheses here. So is it true is bool and X are both 4? Because when we define those at the top, they're both they're both integral types. And that would be the same for nums as well, although we didn't do nums. So my struct1 is struct a struct. That's 8 bytes, 4 for the integers. My struct t is 24 bytes, 4 for the integer, 4 for the Boolean, and then 16 for the character array, the string. My struct3 is 8 bytes because it has 2 integers. And my union is 16 bytes. And the reason for that is, for my union, we don't need to hold them all together. We just need enough room to hold one. So we're never going to use this to hold an integer and a character. We're going to use it to hold an integer or a Boolean or a character. We're not going to use them all at the same time. Now, where is this useful? There's places, especially when you're doing embedded work or if you're working with networks, it's possible, for example, for a network header to have, depending on the version, some particular field in the header means a different thing or has a different type in different versions. And it's not uncommon for network protocols to change as they're used. People learn more about how they're used and they say, okay, version 4 of this network, now instead of an integer here, we're going to have 6-bit set to be whatever value. And so you can have a union that has either one, and then based on the version number of the header, you can decide which one to use. Or if you ever have some memory that you want to hold multiple values at different times, a union will work. Think of it like a backpack. Your backpack doesn't have to be big enough to hold every book you own. It only has to be big enough to hold the books you need for a particular class or a particular day. And then the next day you can come in, take out the books you were using, put in the books for the next day, and it's big enough. As long as it's big enough to hold the most number of books you would ever carry, it'll always be big enough, even though it's not big enough to hold all your books.